Good morning, good afternoon, and good evening. My name is Whitney. Welcome to our third one-hour session of Arista Technology webinar series, Designing and Deploying EVPN VxLAN Networks. Previous topics have been optimizing ARP in EVPN VxLAN and route types and routing models. If you have not seen those episodes or would like to rewatch them, please visit events.arista.com/webinars. Our fourth webinar will be on April 9th, same time, same place, so mark your calendars. Today's topic is multi-homing in EVPN VxLAN deployments with MLAG. Allow me to introduce our speaker, Arista's own system engineer, Mitch Vaughn.
All right, cool. Well, thank you, Whitney, for kicking things off. And yes, we are back for round 3. So thank you again to everyone that has made the time to join this session, as well as those who attended the previous 2. Today, we'll be focusing on multi-homing in EVPN VxLAN deployments with MLAG. But also, here's a nice list of what's still to come. We brought up the active event that'll be on April 9th. And then we'll touch on scaling. And for the grand finale in session 6, we'll wrap the series leveraging some new standards to enable VRF-aware routed multicast in the overlay. Now, during these sessions, we are broadcasting live to all of you, our virtual studio audience. So please ask questions via the Q&A window. We want to make sure that make it as interactive as we can while still trying to adhere to our 1-hour-ish time frame. Now, we made pretty good time last session, but we've got a lot of ground to cover today, so let's see how we do. As a reminder to all, the sessions throughout this series will assume that attendees have an understanding of VxLAN fundamentals and operations. Also, as a note, for those that may be first timers on today, we'll be building upon the concepts covered in the previous sessions. Meaning today, we'll build upon the concepts of the route types, the different routing models, optimizing ARP, so we really won't spend much time discussing any of these in detail. Now, as usual, we'll be going through a series of scenarios to discuss today's topics. And speaking of the topics, here they are. So in order for us to actually optimize our MLAG multi-homing deployment, step 1 is, of course, to deploy MLAG. So we'll kick things off with the review of MLAG, the fundamentals, concepts, and finally, how to configure it. After that, we'll run through a series of scenarios where we explore how to optimize our MLAG multi-homing configuration. For those that may need a refresher on some of the previous topics, yes, we can reach those at events.arista.com, but we can also go to the chat. We can get those posted for everyone just in the chat window to link to. One final note, all of today's scenarios will leverage the symmetric IRB model with selective ARP enabled. But before we jump into the first scenario with no real context around what the environment looks like, let's take a minute and get familiar with our topology. And for those that have attended the first few sessions, this should look pretty familiar as, well, nothing has changed. It is still a layer 3 leaf and spine. And while we certainly have multiple options for building out reachability within the underlay, in this environment, we're using external BGP to provide IP reachability within the underlay, as well as establish peerings within the EVPN address family in the overlay. And also, just as in the previous sessions, the point-to-point links will just serve as transit, and the only time we'll really focus on them is if we want to, for example, perform a packet capture to validate the data plane. So while the point-to-point links aren't of much interest, what is of interest are the loopback interfaces, which we'll be discussing quite a bit today. Loopback 0 on all of the nodes in the topology will uniquely identify each respective node in the topology. It will also serve as the source interface for peerings established in the EVPN address family between the leaf and the spine switches. And we can see here loopback 1, this only exists on our leaf switches, aka our VTEPs, and this will serve as the source interface, well, really the source and destination of VxLAN tunnels. In other words, the address found on this interface is what we'll see in the outer IP header of the VxLAN packets in our packet captures. Now, to save us some time, the environment is pre-configured with just enough to set the stage for our scenarios, meaning that all of the underlay IPv4 peerings and overlay EVPN peerings are already established. On the leaf switches, the VLANs are mapped to VNIs, the VxLAN interfaces have been created. We also have the MAC VRFs already created for the different VLANs. and an IP VRF is created for VRF-A. And again, the environment is pre-configured with the symmetric IRB model with selective ARP enabled. So there's quite a bit pre-configured, but what's missing is any MLAG configuration and any associated optimizations. Thus, Leaf 2A and Leaf 2B are where we're going to spend most of, actually all of our time from a configuration standpoint. But just in some of the other sessions, we'll occasionally use the spines or Leaf 1A in this case for packet captures and control plane state validation. So with that being said, we have the stage set. Let's actually jump into a review of the MLAG fundamentals and configuration, also referred to as multi-chassis link aggregation. Now with MLAG, this is going to enable active-active forwarding on links that are members of an MLAG port channel. And with MLAG, we have two independent devices, each with their own respective control plane. In this case, Leaf 2A and Leaf 2B, we have them appear as one logical switch to their MLAG clients. The peers are configured in what's referred to as an MLAG domain, which can contain a maximum of 2 switches. The value of the MLAG domain ID must match on both peers, but it is locally significant to each respective MLAG domain. The MLAG peers, so once they're in the domain, they will share a common MLAG system ID. Now this MLAG system ID is derived from the chassis MAC of the MLAG peer that has the lowest chassis MAC address. But once it's set, it is a persistent value that remains constant through failover events, reloads, etc. amongst the two MLAG peers. Now this is an important value, the MLAG system ID, because this is what's going to ultimately be used as a shared LACP system ID, spanning tree bridge ID, and as we'll see later, the EVPN router MAC that can be shared amongst the two MLAG peers. Now the MLAG peers are connected together via what's referred to as a peer link, which ultimately is it's a layer 2 port channel trunk between the peers. After that, there's the MLAG VLAN and its associated SVI, and this is used to synchronize layer 2 control plane state and exchange keep lives between the MLAG peers via the peer link. Now, one more thing to touch on before we jump into the environment, any given interface on an MLAG peer is going to fall typically into one of 3 categories. It can be a peer link interface, meaning quite simply that it's just a physical interface that's a member of the peer link port channel. We have the MLAG interfaces, which is any physical interface that's a member of an MLAG port channel. And then last but not least, we have the non-MLAG interfaces. And these are interfaces that are neither members of the peer link, nor are they part of any MLAG port channel. Now, we bring this up because the classification of an interface is important to consider when performing maintenance that requires an MLAG peer to be reloaded. So let's say, for example, let's pick on Leaf 2A. Let's say we reload Leaf 2A for whatever reason. Maybe there's a maintenance event, we're doing an upgrade. When it comes back online, the peer link will immediately transition to a forwarding state once the peer has come back up. Now this means that the peer, in this case Leaf 2A, can synchronize layer 2 control plane state from its peer, Leaf 2B. Additionally, if there is a routing protocol adjacency between the MLAG peers, as we'll see later on today, Leaf 2A will also synchronize layer 3 control plane state. But the MLAG and non-MLAG interfaces are going to be held down by what's referred to as a reload delay timer. And each classification, whether it's MLAG or non-MLAG interface, receives its own respective timer. So these timers, the idea is that they're going to allow us to ensure that interfaces are not transitioned to a forwarding state until the switch has completed the control plane convergence necessary to properly forward traffic. In other words, we don't want to have an interface start forwarding traffic before the switch is actually ready to forward that traffic to its destination. And in our environment here, with our layer 3 leaf and spine deployment, it's recommended that the reload delay timer for non-MLAG interfaces be set to a shorter duration than the MLAG interfaces. And the idea is that this is going to allow the switch to establish its upstream routing protocol adjacencies, in this case via BGP to the spines, and have a steady state forwarding model in place before any of the MLAG interfaces are transitioned to a forwarding state as well. And the idea here is that by the time, let's say the interface towards host C comes online and host C's sending his traffic out the left leg of this port channel, instead of still having these interfaces down and having that traffic destined to a remote VTEP, for example, have to go through the peer link to go to its destination. If interface 1 and 2 on leaf 2A are already up and ready to forward traffic, then it just follows a steady state forwarding model at that point in time. So now that we've gone through some of the fundamentals, some of the concepts, let's take this off of the whiteboard and let's actually go into the environment and start configuring this. And we'll start with just pick it on leaf 2A here. And what we'll do is we'll actually leverage a configuration session for much of our configuration today, which allows us to build a batch of configuration to apply when we're ready. It also gives us the chance to talk through what's going on in the configuration. So here we have VLAN 4094. This is what's going to be referred to as our MLAG VLAN. Notice that it's in a trunk group, and we'll talk more about this in a second. After that, we have the SVI that's going to be used to synchronize control plane state with the MLAG peer. And then notice here that we're disabling spanning tree for VLAN 4094. Now, the reason we're doing this is we don't ever want to be in a position where spanning tree, for whatever reason, blocks VLAN 4094 across the peer link. But of course, if we're going to disable spanning tree for a particular VLAN, in this case 4094, we want to make sure that it's only allowed down trunk links where it's explicitly intended. This is the purpose of the trunk group. So depending on how you look at this, it's an inclusion or exclusion mechanism. But the idea is that the peer link here, port channel 1000, is switch port mode trunk. Now, without this command here, even though switch port mode trunk just says allow everything, VLAN 4094 still would not be allowed down that trunk until that trunk is a member of this trunk group MLAG peer. So in this case, VLAN 4094 is allowed across the peer link so that the MLAG peers can synchronize their control plane state. Next up, we have the MLAG configuration, where again, the domain ID must match on both peers. We're just specifying the local interface that we're going to use to establish the control plane with our peer located at this address. And then we're just calling out this is the peer link. Now after this, this is the physical interface going down to host C. We're placing that into port channel 10. And then under the port channel 10 configuration, we're just specifying that this is a part of MLAG 10. All right, so let's go ahead and paste this into leaf 2A. And before we commit it, let's go ahead and go over to leaf 2B and do the same thing. So we take the configuration, we'll leverage a configuration session. But instead of just pasting this in, it's a very cookie cutter configuration. We need to make sure that we use a different IP address on VLAN 4094. And then of course the peer address is going to point back to leaf 2A. But everything else stays identical. So from an automation standpoint or just a repeatability standpoint, the configuration of MLAG is very cookie cutter. So we can paste this into leaf 2B. We can then commit the changes. And once those changes are committed, assuming that our configuration is correct, we can go ahead and watch and see, okay, the peer link is up. It's in a connecting state right now from an MLAG standpoint. And now the actual MLAG control plane, it's been established. We see here the domain ID, the local interface. This is a lot of the vitals. It's a handy command, just simply show MLAG. Shows us some of the vitals about the MLAG status on this particular device. Now, before we just kind of jump into our next scenario, and we'll pause for questions after this, I do want to show a couple enhancements that have actually saved me a couple times out in the field. In particularly, if we go to the peer link, notice that once we enter in PO 1000, the parser tells us as a warning, hey, just a heads up, this is the peer link. If we try to shut it down, it actually won't let us. Likewise, if we go into the MLAG SVI, okay, by the way, this is the MLAG local interface. We're using this to synchronize the control plane. We can try to shut it down. We can try to change the IP address. Whatever we try here, the point being is there's other protection mechanisms here, but point being is that it's protecting us from potential human error. Or potentially from things that we may not be aware of. So for example, if we go and do show MLAG interface, the peers track each other's interfaces that are part of MLAG port channels. So for example, on leaf 2A, it knows that the remote peer, leaf 2B, his port channel 10 interface is in the up state, it's forwarding. So in other words, it's active full. But let's say we're doing a maintenance event on leaf 2A, we're just upgrading the device, we're gonna have to reload it. What if we didn't know that at some point in time on interface Ethernet 10, which is where host C is connected here, on leaf 2B, if we shut down that interface, now host C is single homed. Well, because the peers are tracking each other's interface state, if we come in here and we go to do that reload after that, where we're doing that upgrade, it gives us a warning and lets us know that, hey, just so you know, before you do the reload, which you still can do if you want, check and make sure that host C actually is able to forward through leaf 2B, because right now it's showing a down state. So we're going to go ahead and cancel the reload because we don't want to do that. We're going to look at that and say, oh, wow, well, let's make sure host C is, in fact, dual homed and operational. So we come over here and we fix the problem. This time it's a pretty easy one. No shut. There we go. But the idea is that there are some protection mechanisms in place to help us from an operational standpoint. All right, so now that we actually have MLAG in place, before jumping into the next scenario, one, let's cover the different topologies, because we've only really seen the single tier so far, and that's all we'll really see today in the lab. But we still wanted to call out that whether it's a square topology or a full mesh, aka bow tie, or a multi-tier topology, all of these are supported, and all of the links that are members of MLAG port channels are in an active, they're in a forwarding state. So next, well, we want to actually enable VxLAN functionality on our MLAG peers. But before we do that, we'll pause for questions. So Alex, any questions out there?
Mitch, just one question there, but just kind of like, I think you're referring to MLAG peer. Do you want to just clarify what we mean by an MLAG peer and an MLAG domain?
Yeah, of course. So if we go ahead, we'll go ahead and hop back to the this slide here. The MLAG domain represents the peering relationship between these two MLAG peers. So an MLAG peer is simply referring to a switch that is configured with for MLAG within a particular MLAG domain. So in this environment, the two MLAG peers would be leaf 2A and leaf 2B. In the relationship between those two MLAG peers, when they synchronize their control plane, they make up MLAG domain 100. And just to kind of reiterate, the domain ID value, it's a string value, but it's ultimately locally significant to that respective MLAG domain. So what I mean by that is, for example, if we have a square topology, if this is MLAG domain 100 and this is MLAG domain 100, that's fine. So from a repeatability standpoint, we can use the same domain ID in multiple locations if we want to. You don't have to, but it is an option. All right, let me know if that answered the question. Was that pretty clear, or do you want to add anything to that, Alex?
I think it's pretty clear. Thanks, Mitch. I think you can move on.
Okay, cool. All right, so next, let's actually get some VSTEP functionality on these MLAG peers. But before we do so, let's talk about how we're going to do that. So remember, the idea with MLAG is that the MLAG peers, in this case 2A and 2B, we want them to present themselves as a single logical switch to their MLAG clients. Well, from a VxLAN standpoint, we want to have the same model where the two devices will also present themselves as a single logical VTEP. So here we have it where loopback 0 is used for BGP peering. And this unique loopback, it's not used for the, we don't want to use it for the VTEP address. That wouldn't be a supported deployment model. Instead, what we want is to enable the MLAG peers to present themselves as a single logical VTEP. And we do this just by a methodology called the shared VTEP IP address. You'll notice that we actually have a new interface here on each MLAG peer, and it's loopback 1, and it's quite simply just 2222/32. It matches on both of the peers. So loopback 0 in this case is dedicated to EVPN peering for BGP, and then loopback 1 is what's actually going to be used as the source of the VxLAN interface on each respective MLAG peer. And what this is going to do, it's going to enable equal cost multipath forwarding from remote VTEPs towards this single logical VTEP. And the reason for that is because when these two devices originate their EVPN updates into BGP, the next hop value is going to be set to the IP address tied to the source of the VxLAN interface, in this case, 2222. So let's go ahead and jump into, let's take this off the whiteboard and into the lab and actually see this in action. But before we actually put the configuration in place, let's actually see what impact it has on the control plane. So first, we're going to go ahead and look for IMET routes. And for the sake of brevity today, we're going to just focus on looking at the IMET routes in the control plane. So we'll look at the type 3 route for VNI 10,010 from the perspective of spine 1. And right now it sees, as expected, the IMAT route that was originated by leaf 1A. Leaf 2A and 2B aren't VTEPs yet, so we'll see their control plane state populated in here shortly. But on leaf 1A, let's also look at the flood list. So the actual VTEP flood list that'll be populated by those type 3 routes. So right now there's just a whole lot of nothing. Well, let's go ahead and go over to leaf 2A and 2B and get the shared VTEP IP address configured. In the configuration here, we're going to create loopback 1, add a description because we're good network citizens, and then add IP address 2222/32. And this configuration is going to be identical on both MLAG peers. Under the interface VxLAN 1, we're going to make sure that the source interface is going to be set to loopback 1. So we'll paste in this configuration here. And we'll go ahead and commit the change. And what we should see is that once this change is committed, these two devices are now VTEPs, but ideally they'll be presenting themselves as a single logical VTEP, which is exactly what we see here. Notice that we still have each VTEP's own unique IMAT route, but the next hop on each respective update is the shared logical VTEP IP address of 2222. Likewise, on leaf 1A, we see that it noticed via the type 3 route that, oh, well, there is a remote VTEP that has advertised interest in receiving BUM traffic associated with these respective bridge domains. So at this point, we have the two MLAG peers presenting themselves as a single logical VTEP to the EVPN domain. But if we look back at the spine here, the question then becomes, since the contents of each MLAG peer's EVPN update is identical, should we set the route distinguisher to a common value in order to save on control plane state or not? And we're going to explore this next, but before we do, we'll again pause for any questions on this. So Alex, any questions out there?
Yeah, I think there's been, sorry, Mitch. Yeah, so one question was, you've talked a little bit MLAG, and so the MLAG and the concept of EVPN, I mean, what does that mean in terms of remote devices? How do they understand? Is there any proprietariness in terms of the remote device, in terms of how we implement this? So
yeah. Let's. I'll take a stab at answering the question. Let me know if there's anything that I miss here. But let's go ahead and go back to our topology really quick, and we'll kind of whiteboard this out. So here, if we have, let's go back to the full topology. So like host C, for example, if host C sends a frame this way, whichever direction, these two devices presenting themselves as a single logical VTEP, there's nothing proprietary going on here. What's happening is that the next hop field in the EVPN update is going to be set to whatever loopback is set as the source of the VxLAN interface. In this case, we're just making it match on both of the peers. But the actual route that's generated, let's say, for example, it's a type 2, just a MAC route for host C. By the time leaf 1A receives that, there's nothing inside of that route, that control plane state, that actually shows that, hey, this came from an MLAG device, or you're actually performing a VxLAN bridging or routing operation to a remote VTEP that is an MLAG peer. From the perspective of leaf 1A, if we look back at that control plane state, and we can look at it in a bit more detail, let's go ahead and look at the IMAT route in some more detail here. Notice that there's nothing in here. These are the usual suspects of our EVPN control plane state, particularly for a type 3 route. There's nothing in here that indicates whether or not it was from an MLAG peer. The idea is that we just had the shared VTEP IP address so that we can have the ECMP forwarding from leaf 1A, for example, in order to reach the remote VTEP of 2222. So Alex, do you think that adequately answers the question, or is there anything you'd like to add to that?
No, I think you cleared. I mean, the point being here, to leaf 1A, it doesn't know that this is an MLAG on the remote end. So from an EVPN perspective, it just sees it as a single NIC top, right? So there's no change there. That leaf A, obviously, in this diagram here, it's our switch, but it could be a third-party switch, right? It's completely abstract to the way the MLAG.
Correct. Yep.
Okay. Thanks, Mitch.
Cool. Yeah, no problem. All right, so we are moving right along here. Let's jump into that route distinguisher question we just asked a few minutes ago. And the question being, now that we have the shared VTEP IP address, from a VxLAN standpoint, leaf 2A and leaf 2B appear to be a single logical VTEP. But notice that in the control plane state, we could still tell where a route was originating from because each peer, each MLAG peer, had a unique route distinguisher. So what happens if we make this a common value? So let's say, for example, we have 2A and 2B, and they're advertising a type 2 route for host C. In this case, the route distinguisher associated with the MAC VRF that host C resides in is the same on leaf 2A and on leaf 2B. So what happens is that leaf 2A, and we'll focus on spine 1 just for the sake of simplicity here, it advertises its type 2 route to spine 1, and then 2B does the same, its copy of this particular type 2 route. Now, once spine 1 receives this, with the identical route distinguishers, it really doesn't have a way to differentiate between the two entries in the BGP rib. So it just says, oh, wait, well, I have to run best path on this. These are two of the exact same route. So I have this one that came from 2B, this one that came from 2A. Which one am I going to choose as the best path? And then forward on, in this case, to leaf 1A. And we'll say for the sake of this example, it chooses leaf 2A's update. So now what happens is spine 1 will then advertise leaf 2A's update over to leaf 1A. And ultimately, spine 2 will do the same. So at this point, leaf 2A has two copies of the type 2 route in its BGP rib, but it really doesn't have any, we can't really tell who ultimately originated that control plane state. Now, after this, the usual suspects, it's going to end up in the BGP rib, it'll be promoted to the fib, and we'll have a forwarding entry. But the part of the challenge here is that while we do have reduced control plane state versus what we're going to talk about in a second, again, from a troubleshooting standpoint, we can't really tell where the route really originated from, but also there is an impact from a conversion standpoint that we're going to touch on in a second too. So looking at that same scenario, now we have unique route distinguishers on each respective MLAG peer. So leaf 2A is using its value that's mapped to loopback 0, in this case 11121, and leaf 2B, same thing, 11122, the value associated with its loopback 0 address. So the point being is that the route distinguishers are now unique. So what happens, walking through that scenario again, leaf 2A advertises the type 2 route to spine 1, as does leaf 2B. But now spine 1 can say, oh, well, these are each their own unique route. These are separate entries. So what is the best path for what was advertised from leaf 2B? It's a pretty easy choice. It's this guy. And from leaf 2A, oh, this guy. So what will happen is it will then advertise both of those updates down to leaf 1A. And also spine 2 will repeat the same process. It'll send the route received from leaf 2A and the route received from leaf 2B. So now we can see out of the gate that this is going to result in some increased control plane state that's going to be relative to the number of spines that we actually have in the environment operating either as route servers or route reflectors. So now that leaf 1A has 4 copies of this type 2 route in its BGP rib, ultimately something's going to be promoted to the fib for the forwarding entry. But if we look at this now from a troubleshooting standpoint, with each route having a unique route distinguisher applied to it, we have the ability to perform some troubleshooting and say, show me all of the IMET routes that originated from leaf 2B for VNI 10,010, which can be helpful when we're trying to validate, is this remote VTEP behaving as expected or not? Also, from a conversion standpoint, let's say, for example, leaf 2A has been a good sport. We'll stick with them. Let's say we're going to reload leaf 2A. We're upgrading, something's happening. What will happen is leaf 2A's routes are going to be, of course, withdrawn from the environment via BGP. Now, in our previous example, if the routes are withdrawn, then it's at that point in time, these spines will have to promote the leaf 2B's update to the best path and then advertise that down to leaf 1A, which from there, it'll be placed into the rib and then ultimately into the fib. But in this scenario where we have the unique route distinguishers, the routes are already there on leaf 1A. So immediately, once those other routes are withdrawn, we're going to go ahead and have the forwarding entry updated. The actual information on the forwarding entry is going to be the same, but the idea is that from a control plane standpoint, we already had the other routes in the BGP rib already. Now, in our lab today, in the environment we're playing around in here, the difference in convergence time is negligible. But in a production environment where you may have thousands of hosts and or thousands of VNIs, this can end up making a pretty big difference. So before we take this from the whiteboard into the lab, just a quick summary on the route distinguishers again. With the identical route distinguishers, there is reduced control plane state. With the unique route distinguishers, we do see more control plane state relative to the number of spines or route reflectors that are located in the environment. But we do see, trade-off is that we do see improved convergence time, and we also have the ability to validate remote VTEP route origination. Okay, so let's go ahead and take this over to the lab and actually configure it and see it in action. So what we'll do is right now, let's actually take a look at the control plane state information on Leaf 1A. So we'll keep picking on him. So right now we see that we have the IMET routes, the type 3 routes, from Leaf 2A and Leaf 2B. We know that this is from Leaf 2A, one copy from spine 1, one copy from spine 2. Likewise, from Leaf 2B, we have those routes, one copy from spine 1, one copy from spine 2. So 4 total, just as we covered in our example. Let's go back here to Leaf 2A, and let's actually use a config session on 2A and 2B, and let's set the route distinguisher on the MAC VRF and BGP to be a identical value. So we're just going to go into the BGP process. We're going to go VLAN aware bundle. So this is our MAC VRF for tenant A. And then we're going to set the route distinguisher to an identical value on both of the MLAG peers. Leaf 2A. And then, of course, Leaf 2B. What we're going to do here is, just so we can see the difference in the control plane in real time, we're going to put a timer on this commit. So before we just say, yeah, commit the change and then manually roll it back, we're just going to say, hey, if switch, if you don't hear from us in 10 seconds, go ahead and roll this change back. So it'll roll it back to where it was prior to this particular config session. So let's go ahead and go over here, commit timer, same thing, 10 seconds. And then now if we go to Leaf 1A, once we apply this, we should see the control plane state change so that it's going to be reduced without the unique route distinguishers. And then it's going to be increased once this change rolls back and we have the unique route distinguishers again. So we can kind of watch this in real time. Let's go ahead and apply the configuration, come back here to Leaf 1A, and we have the watch command running here, and we see the control plane state changes. Now we have the 2 entries, but we really don't have a way to validate where do those entries actually originate. We know we got one from each respective spine. The next hop is always the same regardless of the model deployed, but here there's really no way for us to validate, did we actually receive an IMET route from Leaf 2B for VNI 10,010? So now that the configuration session timed out and it rolled back to our unique route distinguisher configuration, we can see here that, okay, we have them all back and we can clearly see who's originating what. But let's say we're in a position where we got to troubleshoot, and let's say we can say, show BGP EVPN route type, show me the IMET routes associated with Leaf 2B, which we know is this route distinguisher, for VNI 10,010. Or in other words, is Leaf 2B advertising interest in receiving bump traffic for VNI 10,010? We can see here that it is. With the identical route distinguishers, we don't have the ability to do that from a troubleshooting standpoint. So before we move on here to our next scenario, which is where we're going to touch on the Anycast gateway redundancy, let's go ahead and pause for questions. So Alex, anything outstanding out there from a question standpoint?
No, I think we're good. The only thing that's been asked, Mitch, was like in your demo setup, I didn't want to sort of preempt it, but someone's asked the question of what code are you actually running with these features?
Oh, sure. Yeah, in the demo, actually here, I can show you guys. So here, we're just, we're running on a 7280 SR platform and the code base is 423.1F.
I think we're good, Mitch. You move on.
Okay, cool. All right, we are moving right along here. So the next scenario, Anycast gateway. The idea here is that now that we have the MLAG peers presenting themselves, of course, as a single logical switch to their MLAG clients, but also as a single logical VTEPs to the EVPN domain, then now we have the question of what do we do for our gateway redundancy amongst the MLAG peers, and actually also this will work on devices that don't have MLAG running either. So the idea here is from a first hop, redundancy protocol here, a gateway redundancy protocol, we can use something like virtual ARP, we can use VRRP, but the recommendation in this particular scenario where we have a bunch of top of rack switches that we just want to share the same IP address, gateway IP address, and the same gateway MAC address, is we can use the IP address virtual command on the SVIs of the VTEPs. So we'll pick on VLAN 10 here, and we can see that the gateway IP address for VLAN 10 and the gateway MAC address is consistent across all of the top of rack switches in the environment. So this isn't really MLAG specific, but it is something that we do want to have running on our MLAG peers from an optimization standpoint. And the reasons why we would do this is that we're going to conserve IP space. So in a deployment where we have let's say we have hundreds of top of rack switches, and we want to share a common gateway IP address across all of them and a gateway MAC address, rather than needing to burn a physical, as I make air quotes, a physical IP address on the SVI of each respective top of rack switch or VTEP. With this model, we only need to have the virtual IP address applied to the SVI. So it's going to give us that conserve the IP space, but it's also going to give us a very repeatable configuration. So back to automation, just looking at how many variables do we need to deploy something like this, the configuration of IP address virtual and ultimately the SVIs becomes very cookie cutter. So if we take this and we look at it from the actual CLI here, let's pick on leaf 1A, 2A, and 2B. And let's just simply do show run in VLAN 10. We'll keep picking on him. Okay. So as we click between these guys on the different tabs, it's the exact same configuration. And then also from a gateway MAC standpoint, if we look at the virtual router MAC address that's defined on these nodes, they are all using the same MAC address for the gateway MAC across all of the SVIs. So it's a consistent model. So when hosts are moving around within a data center, between data centers, ultimately between different VTEPs, as long as that VTEP is running IP address virtual and its gateway IP address and MAC address is consistent with what's deployed on the other VTEPs, hosts can now move around the environment without the need to actually refresh their local ARP cache to reach their gateway. So that one in particular, there's really not much more to show. Alex, I do want to pause for questions before we jump into the next one, because this one may take a little while. Any questions out there?
Sorry, Mitch. Yeah, just one. It just popped up there. So just kind of covering the virtual MAC. So
yeah.
I don't know if you explained there. I think the question was, do we have to manually configure that or not? How is it done?
Yes, good question. So over here, that was manually configured. Over here, if I want it to be consistently the same MAC address across all of the devices, this configuration, show run, I just did a quick grep, case insensitive, for virtual router MAC address. And in the global configuration context, we define the configuration IP virtual router MAC address. And then in this case, it was just ABC. You can ultimately make this any valid MAC address. Cool. Any other questions out there, Alex?
No, I think we're good. We can move on, Mitch. Thanks.
Okay, cool. All right, so next up, let's go ahead and jump into the shared EVPN router MAC. And we'll kind of set the stage here showing like what's happening without this particular feature enabled. So we'll walk through a scenario where host A wants to ping host C. Now you've seen that we have the MLAG peers in their respective MLAG domain. MLAG's up and operational. Host C is dual homed. It's happy that MLAG port channel's up. It's good. The devices are presenting themselves as a single logical VTEP to the EVPN domain from a layer 3 standpoint, but they're currently using their chassis MAC address in the advertisements of their dual VNI type 2s and their type 5 routes. Meaning that when leaf 1A, when host A wants to ping host C, leaf 1A is going to use one of the routes that were originated by leaf 2A or 2B. It's going to say, oh, well, I know the next hop, the destination egress VTEP to reach host C is 2222. And now remember, in the symmetric IRB model, leaf 1A is not bridging, it's not doing VxLAN bridging towards host C, it's performing a routing operation to the next hop VTEP that advertised reachability to that particular host, in this case, host C. So let's say it followed, if for whatever reason it followed the update that originated via leaf 2B, and the EVPN router MAC in that update ended in Alpha 7 Foxtrot Delta. Well, then if it lands on leaf 2A, so leaf 1A puts in the outer IP header the logical VTEP IP address, which we know is going to use equal cost multipathing, and it could land on leaf 2A or leaf 2B. Either one is fine. But let's say for the sake of the example, it lands on leaf 2A. When 2A receives this packet and performs a decap operation on it, it is going to inspect the inner Ethernet header, in particular the destination MAC address. And it's going to see that the destination MAC address is actually the MAC address of its MLAG peer, in this case, leaf 2B. So because of that, what it will do is forward the packet across the peer link, arrive at leaf 2B, who will then perform the local routing operation into the destination subnet, and then ultimately bridge to host C. But the point here is that it isn't that nothing's broken in this particular scenario. Reachability is there, the communication exists. It's just suboptimal forwarding. And so the question becomes, how do we address this? And we're going to go right back to that value we talked about quite a bit earlier, the MLAG system ID. So one of the things that we can do is have leaf 2A and leaf 2B, when they originate their dual VNI type 2s or their type 5 routes, for example, they will apply the value of the MLAG system ID as the EVPN router MAC in the payload of that particular route. So going through that same scenario, host A wants to ping host C. Leaf 1A now, okay, well, it's going to follow via the next hop in that route the path to 2222. Equal cost multipathing, we know it can land on either particular MLAG peer. Let's say it lands in, at this point in time, it could land on leaf 2A, it could land on leaf 2B. It really doesn't matter because once, let's say leaf 2A receives it. Once it receives it, performs the decap operation again, it looks at the inner Ethernet header, in particular the destination MAC address, which we see was set to the MLAG system ID, which leaf 2A will act upon and then perform the local routing operation into the destination subnet and ultimately bridge to host C. So in other words, we're no longer going to be in a position where leaf 2A needs to use the peer link for whatever reason to reach host C. It can perform that local routing and bridging operation itself because the EVPN router MAC is set as the MLAG system ID. So just as we did with the other examples, let's go ahead and take this one into the lab and see it in action. But before we do that, let's go ahead and before we configure it, let's hop on leaf 1A, and we'll keep using them to validate control plane state. We'll clean up our screen here. And right now, there is nothing there, which is expected here. So let's go ahead and get host A pinging host C. All right, pings are running. And if we look back at leaf 1A, our control plane state populated via the dual VNI type 2 routes that were originated by leaf 2A and 2B for host C. Notice that the next hop VTEP is the same, the layer 3 VNI is the same. That's all well and good, but each update has a unique router MAC. And then we can tell that this is the chassis MAC address of leaf 2B. This is the chassis MAC address of leaf 2A. What we'd rather have here is, let's have this set to the MLAG system ID of the MLAG peers, so that way, regardless of which one receives the VxLAN packet, it can perform the local forwarding operation to the multi-homed host, in this case, host C. So let's go ahead and get this configured up and hop into the EVPN router MAC here on leaf 2A and 2B. Again, we'll use a configuration session. And what we'll do is we'll go under the VxLAN 1 interface, and we'll enter the command VxLAN virtual router, encapsulation MAC address, MLAG system ID. So we'll do this on leaf 2A, and then we'll also put it into place on leaf 2B. We'll commit the change, and then once it's committed, what we should see, hopefully we can catch it in time. There we go. we see that now there's one entry here, and it points to, again, the shared VTEP IP address, the layer 3 VNI, but now the router MAC is the EVPN router MAC that was advertised by Leaf 2A and 2B, which both of them are using the MLAG system ID for that field now in the payload of the route. So I know that's quite a bit to cover. I do want to pause for questions before moving into the next scenario. So Alex, is there anything out there from a question standpoint outstanding?
Yeah, so one question was regarding when we start using the shared router MAC, how does that affect ECMP?
Okay, good question. So ECMP is actually going to remain, in this case, it won't be impacted because ultimately Leaf 1A, regardless of the EVPN router MAC that's used in the payload, that's going to be used after VxLAN decap on the remote VTEP to determine, okay, do I need to act upon this frame or not? But actually getting the VxLAN packet to the remote VTEP, we're still going to follow the path towards 2222. So in other words, Leaf 1A, ultimately, when it performs that VxLAN routing operation towards the remote VTEP, which it believes is just 2222, it's just going to do exactly that. How do I get to 2222? And it's still going to use ECMP in the underlay to reach that logical VTEP, which we know could end up being Leaf 2A or 2B. The shared EVPN router MAC is really going to only have an impact within the local MLAG domain between the peers themselves. And it's the whether or not we have the chance of having a suboptimal forwarding scenario where we're using the peer link, or if we're using the shared EVPN router MAC, then we can just locally forward. We can say with confidence that we'll locally forward that packet to the destination host. So I know that was a bit of a mouthful, Alex. I think I answered the question. Anything else you want to add?
Yeah, no, that's good. I think one other question, and I think you might cover this later on anyway. So if you do, just leave it out. So one question was asking, when we're doing these pings, how are we actually generating the ping given the fact that we have our shared Anycast gateway here? I think you covered this later on in the demo, but I don't know if this is the point where you want to cover this or you want to cover this later on.
Oh, sure. Yeah, we will cover it later on. But for the sake of these pings here, this is just coming from just a little Raspberry Pi behind the scenes, host A, generating the pings into the environment. But as far as pings from the switches themselves, is that more the question, or is it just how are these pings happening from host A?
Yeah, I think someone asked, one question was exactly what you just, so these are the Raspberry Pi, the end hosts. The other question was if we were having it, once you generate a ping from Leaf itself, given the fact that we have Anycast gateways and they're shared across all the Leafs, how do we generate and get a ping coming back to that particular device?
Okay, yep, gotcha. So we are going to cover that in a bit more detail later, but the idea is that it's a good question because now we have a scenario where, we'll cover this real quick before we actually jump into the next scenario. Because now we have a scenario where, for example, we'll go back to our main topology here. Let's say Leaf 1A wants to ping host C, right? Or host E or D, one of those. But the problem is going to be, well, it's the same IP address across all of the SVIs, across all the top of rack switches, all the VTEPs. So the echo request will make it there just fine to host C. The echo reply is destined to, in this case, 30.30.30.1, which, regardless of which way it hashes here, either 2A or 2B, they're going to consume that. They're going to say, oh, this is for me, thank you. That echo reply is going to stop there. In other words, it won't make it back to Leaf 1A. So if we just execute the ping from the SVI, it looks like, hey, that remote host, is it down? What's going on here? One of the ways that we can address this, and we're going to talk about this a little bit later, is we can actually have a unique loopback on Leaf 1A in VRFA, which is the VRF that host C resides in. And then the ping can be sourced from that particular loopback, so we can validate that the data plane is good from the VTEP Leaf 1A all the way to host C. So in other words, we would just source the ping from a loopback in VRFA that's unique to Leaf 1A, and then ultimately it would make it down here to host C, and instead of the reply coming back to .1, it would ultimately go back to the loopback IP address it was sourced from, which would then follow the path back to Leaf 1A, and the ping would work. Well, that's a good question because it's, we have the same IP address across all these top of rack switches. How would the pings work to remote hosts? And without sourcing it from a specific loopback, it's either one, not going to work, or two, we have a 50-50 chance. Like, let's say we're pinging from Leaf 2A. Echo request goes this way. Does the reply come back here, or does it go here? If it goes here, we won't see it. So the answer to that is really that loopback in the VRF. So Alex, do you think that provided enough detail? Anything you want to add to that? You out there, Alex? You may be muted, sir.
Yes, I am muted. I've been
All right.
talking for a while. Yeah, so yeah, it's just in summary there. So the idea here is that each leaf would have a dedicated loopback, and that loopback would be in the VRF, and that's then used as a source of any pings that you were generating from that particular leaf device. Just to summarize, Mitch, what you just covered.
All right,
so we're good.
Perfect.
We can move on. Thanks.
Thank you, sir. All right, next up, peering in the underlay. I think a few questions alluded to this earlier, so let's go ahead and jump in and cover it. Right now, between the two MLAG peers, 2A and 2B, we have the MLAG peer link, we have VLAN 4094, and the SVI associated with VLAN 4094 is synchronizing the layer 2 control plane state between the MLAG peers. So then the question becomes, what about the layer 3 control plane state? What about reachability in the underlay? In order to maintain reachability in the underlay, in a scenario where, for example, these interfaces go down on leaf 2A for some reason, in order for leaf 2A to be able to maintain, one, its EVPN peering sessions with the spines, and two, reachability to remote VTEPs, the underlay prefixes need to be reachable. In this case, if we have an IBGP session in the IPv4 unicast address family in the underlay, then leaf 2A, even if it loses these two links here, it can still maintain its EVPN peering sessions with the spines, but it can also maintain reachability to remote VTEPs, should it need to perform a VxLAN endcap operation towards those particular VTEPs. So the scenario here, we'll actually walk through this. We'll fail the links on leaf 2A, and then we'll be able to actually see the impact that this peering has between the MLAG peers. And to really, the question becomes, can host A still reach host C and host E in the event that those northbound links have failed? In host C, maybe host C, for whatever reason, it's hashing it. Maybe the echo request in this case is going to come this way for the ping. But what if the reply comes this way? Then this device will need to be capable of performing the VxLAN encapsulation operation and then forwarding it to the remote VTEP IP address of 2221. All of that is going to require the EVPN control plane state via the peering with the spines and the ability to reach 2221, which is going to be via again, through leaf 2B, using that underlay peering IBGP between the peers. So let's actually go ahead and configure this, and then we'll fail these links and we'll see the impact it has on the forwarding operations. All right, so jumping back in the lab here, let's go back to leaf 2A and leaf 2B. We'll clean the screens up a little bit here. All right, so what we'll do is first we'll actually get that peering in place. On leaf 2A, if we look at the configuration that we're applying here, we'll just walk through it really quick. We want to use a separate SVI, VLAN and SVI from the MLAG VLAN. Just from an operational standpoint, as you saw, we really can't shut down or change the IP address, et cetera, of anything really related to MLAG. So from an operational standpoint, troubleshooting, it's recommended to use a separate SVI across the peer link for this IBGP peering in the underlay. After that, we're just defining the neighbor in BGP. And let's actually go ahead and apply this to 2A. And then 2B is going to be similar, just different IP addresses. Make sure he's got a different IP address that points to 2A. And then now, once we commit this change, we should see that there is going to be a IBGP peering in the underlay between the MLAG peers. So let's do a launch one show IPBGP summary. I was hoping we catch it in time. You kind of see it. It's only been up for 6 seconds. But now we have the peering between the MLAG peers and the underlay, and we can see that they are advertising and receiving control plane state. Okay, so now with this in place, let's go ahead and take a look at, so right now host A is pinging host C. Tell you what, let's actually use a packet capture on the peer link on leaf 2B, and we'll, let's go and make sure that monitor session's in place here. All right, yep, so we have a monitor session on port channel 1. We're kicking the output of that monitoring session to the CPU. So in other words, we're going to be able to capture the data plane from a packet capture standpoint. So let's see what's going across the peer link right now before we actually do this, before we cause this failure. All right, we're going to send the output of this capture back to our local workstation in Wireshark. All right, so we'll go ahead and make sure that we have access, put in our password. And then also to cut out some of the noise in Wireshark, we're going to apply a filter because there's lots of stuff going on here. Right now on the peer link, we see a whole lot of nothing. So let's go back into the environment and leave 2A, which based on that output, and it's really, it's a chance, right? Because it's the shared MLAG VTEP IP. In this case, it looks like leaf 1A is actually sending the traffic, the VxLAN packet to 2A, locally forwarding it to host C, and then host C is replying by sending the packet back out the left leg of its port channel to 2A, which then makes it to leaf 1A. The result of that is, of course, we're not seeing anything on the peer link. So if we go over to 2A now, and let's do a config session here. So conf session, and let's do interface E1 to 2. Let's shut these down, and let's commit these. Timer. Let's do the 10-second commit again. So if the switch doesn't hear from us in 10 seconds, it'll roll the change back. So we can kind of see in our packet capture, do we start to see the actual pings going across the peer link? And then after this change is rolled back, do they stop? So assuming our configuration has been correct so far, we should see this output on the peer link. So let's go ahead and shut the interfaces down and see that even though those interfaces are down, host A can still ping host C. If we come back here, we now see that the pings are using the peer link. In this case, we're just seeing the reply. Just kind of like a bonus question, why would that be? So we're only seeing the reply here because the request is being sent from host A to leaf 2B. It performs the decap operation and says, oh, the EVPN router MAC is the MLAG system ID. I'm going to forward this. Sends the request to host C. Host C then crafts the echo reply, which it decides to hash over to 2A. And now we see the reply going across the peer link because 2A's interfaces to the spine are currently in a down state. At this point in time, we should have seen it stop, and we did. There's no more pings coming in here because the change rolled back after 10 seconds. But during that outage interval, we could see here that we have the pings going across the peer link, and notice that they're VxLAN encapsulated. So meaning that what happened here is that leaf 2A received the echo request, locally performed the VxLAN encapsulation operation, and then forwarded it through leaf 2B over to leaf 1A. Leaf 1A then does the decap and then forwards it on its way. But the VxLAN encap operation in this case did happen on leaf 2A, and the only reason that works is because one, it still has the EVPN peerings with the spine, so it still has the necessary control plane state to make this decision. And then two, once the decision is made to forward to leaf 1A, it has reachability to loop back one on leaf 1A because of that peering between leaf 2A and 2B in the underlay. So that was quite a bit in that scenario. Let's go ahead and again, we'll stop the packet capture, but we'll also pause for questions. So Alex, any outstanding questions out there?
Surprisingly, no at this point in time, but yeah, carry on with the packet capture and see if there any more comes in.
Okay, cool. So go ahead and close this one out. And then we'll jump over to the next scenario, which I see we're getting close to time here. So again, we're trying to adhere to our 1 hour-ish time frame. In the interest of time, we'll go ahead and we'll talk through this particular scenario. And then for our last scenario, we're actually going to have some fun and we'll break some stuff and put our little configuration optimizations to the test that we've done today. So scenario 6, we have a single homed, in this case, a single homed router connected to one of the MLAG peers, in this case, leaf 2B. And it's advertising the prefix 100/24. And when leaf 2B receives this, it then originates the type 5 EVPN update, the IP prefix route, into the EVPN control plane. And when it does that, it uses the usual suspects, right? We have the shared VTEP IP address, the layer 3 VNI, and we also have the shared EVPN router map, which maps to the MLAG system ID. Now, this is all well and good, but the trouble that we could find ourselves in is what if we do not have a peering with the MLAG peer in VRFA? So before we had the IPv4 unicast peering in the underlay, this is an IPv4 unicast peering in an overlay VRF. And the reason this is necessary is because what if we find ourselves in a situation where from a control plane standpoint, this is what's happening. But then from a data plane standpoint, the traffic that's destined to 100/24, the destination IP address of the VTEP is going to be 2222. The destination MAC in the inner Ethernet header is going to be the shared EVPN router MAC. So in other words, Leaf 2A is going to act upon this frame once it sees that that is the destination MAC in the inner Ethernet header. In other words, it's going to perform a local forwarding operation, and if it doesn't know about 100/24, it'll drop the packet. It won't know what to do with it. So this peering between the MLAG peers and the overlay VRF helps prevent this from happening, because now 2A, via this peering, knows about 100/24 from Leaf 2B, sends it over to Leaf 2B, and then forwards it down to router 1 in this case. Now, alternatively, we can enable a feature referred to as the multi-VTEP MLAG feature. And what this is going to do on Leaf 2B is it's going to say that, okay, well, I have this router single home connected to me. When I receive the 100/24 route from this particular device, when originating the type 5 route into the EVPN control plane, instead of using the shared VTEP IP or the shared EVPN router MAC, instead still use a layer 3 VNI, here's the prefix, but use the unique IP address for this VTEP and use the unique chassis MAC address. And from a data plane standpoint, what this means is that Leaf 2A will never be in the data plane for this particular traffic, because the outer IP header of the VxLAN packets that are ultimately destined to the 100/24 that exists somewhere behind router 1, the outer IP header destination IP is going to be Leaf 2B. In the inner Ethernet header, it's going to be in the destination MAC address field, Leaf 2B's chassis MAC address. Meaning Leaf 2A is never going to be in the data plane for this traffic, because Leaf 2B originated the Type 5 update and essentially told the control plane, hey, if you want to get here, come through me, not the logical VTEP that I share with my MLAG peer. All right, so before we wrap this up by breaking some stuff, any questions out there, Alex, on that scenario?
Less on that scenario, more just on the setup, Mitch. So one of the questions was really the BGP configuration within the MLAG domain, right? So in terms of AS numbers, I know in our setup, your setup there, right? You have the 2 leafs in the MLAG domain, 2A and 2B. They're in the same AS, and therefore you have an IBGP session on that peer link, right, for redundancy and then delay.
Correct.
The other option of that doing, I mean, the argument with that type of model is that the S now sort of signifies the leafs, or the MLAG domain, if you want to think about it. The other potential, and we support it as well, is you could have each leaf in a separate AS, and then you could then you would run an eBGP session across the peer link. Oh, that was kind of one of the questions. But in this setup, Mitch, you're running an IBGP session, correct?
That's correct. Yeah, let's actually go back and look at the topology real quick here. I'm going to show it. Spoiler alert, here's what we're going to break. But yes, that's in this topology. It's the spines are in a common autonomous system, and then the each either pair of leaves or single home leaf is in its own respective AS. So it's IBGP peering between the between leaf 2A and 2B.
And just one final thing, Mitch, before we get into the weeds there. Again, it's based on the BGP configuration. So in our model, we're running each leaf, or MLAG leaf, if you want to call it, is in their own AS. So and the spines are in a separate AS. So we're running eBGP in this configuration. But again, there is an option. If you prefer it, you could also run iBGP where you have a root reflector in the spine. But in their module, we're running eBGP across the fabric.
Okay, yep, correct. Yeah, and either model supported. In this case, we just opted for external for eBGP.
Okay, thanks, Mitch.
Yeah, no problem. All right, so let's get this party started. Let's actually start breaking some stuff. So what we're going to do here is let's go ahead and make sure that host A is still pinging host C, and it is. That's good. So we're going to just do a reload, just see you later, leave 2A and spine 2. But before we do that, to make sure it's a valid test, kind of nothing up my sleeve here, let's make sure that when we do this that we're actually going to impact the steady state data plane for these pings. So on leaf 2A, the way we'll do this is let's do show run section monitor. And we're looking at, okay, so source E1 and E2, aka the spine facing interfaces. Let's do a packet capture based upon that monitor session and see if we're seeing either the echo reply or the echo request and of that ping, then we know that leaf 2A is currently in the data plane for those pings. So let's go ahead and go up here and we'll change this to 33, which is the IP of leaf 2A. And of course, it's going to get noisy, so let's actually apply our filter. All right. Aha. So we see the echo reply. So the request is going through leaf 2B, but host C, when it replies, it's going through leaf 2A. Actually, let's take this a step further. Let's look at the outer Ethernet header so we can see which spine it's destined to. 285 Foxtrot. Let's pinpoint that guy. It's not you. That leaves one. 285 Foxtrot. Okay, so now we know that leaf 2A and spine 2 are both in the data plane for this communication right now. So let's go over to 2A. We're going to be good network citizens and save our config on these boxes. And 2B, and we'll watch these pings, and then what we'll do here is we're actually going to just say, see you later. And what should happen here is that as long as we have our configuration properly in place, the ping should keep rolling because, again, we're using the shared VTEP IP. We're using the shared EVPN router MAC. We have the peering between the nodes. There's all of our optimizations at the end of the day when we do this reload on spine 2 and leaf 2A, and we should see that we're going to lose connectivity to those hosts, and we should lose host E as well. There we go, because host E, behind the scenes, it was just an SSH session from leaf 2A, who's now gone. So E's down, but look at this, the pings were still rolling. So host A is still able to communicate with host C, even though we just took 2 of those nodes that were in the data plane previously out of the picture, and we didn't lose a ping along the way. So this kind of shows that our optimizations, they got the job done. We were able to essentially pull power on 2 nodes without warning in the environment, and we didn't even drop a ping from host A communicating with host C. So go us, our optimizations worked. Let's see if we go back here and look at what's coming next. As we've covered, on the 9th of April, we're going to cover another multi-homing methodology via the active-active ESI model. But before we actually close out the webinar, I do want to take some time here. Are there any other outstanding questions, Alex?
No, I think we've covered most questions. I think couple of questions that we haven't responded to are more in relation to like what's the pros and cons, right, of MLAG against EVPN active-active or all active, if you want to call it. I think to answer that question, you really have to kind of wait for the next webinar when we actually talk about all active, how it works, its implementation, and then I think at that point in time it's good to then address the question, right, of the pros and cons against one against the other. So that's the only really outstanding questions, Mitch, but I think we can leave that to the next session.
Okay, great. Well, in that case, Whitney, back over to you.
That's all the time we have. Thank you so much for joining us today. If we did not get to your questions, please feel free to email us at webinars@arista.com. Recording of this webinar will be available on our website.